So hi. So the topic of this workshop is to EMG signal simulation, and we will talk about solution of EMG signal. So imagine that we have a real EMG signal, and we create the new decomposition algorithm. We want to see how it works, if it can decompose the signal well or not, and we expect to get the shape of motor unit, action potential in different locations that we place the electrode, and the firing rate of each one of the motor units as a result of the composition algorithm. But unfortunately, we don't know that this is the result or valid or not because we don't know the ground truth. And in here, we need to use simulated EMG signal and use our algorithm that we developed for the decomposition, tested on the simulated signal, getting these again the shape of motor unit in each one of the channel and the firing rate of them. And here we know the ground truth. We can check how the algorithms work, estimate the performance, evaluate it, and generally at the time that we get the results of the composition, if we are happy about the result, we can go and use the algorithm on the real signal. But if we are not happy, we need to improve the decomposition algorithm. And usually it's like that. If the decomposition signal works well on the simulated signal, we have the confidence to use it on the real signal, and we hope to get some meaningful result. But if it is not really work well on the simulated, we need to improve because otherwise it's not going to work on the real EMG signal. Of course, in this workshop, we are focusing on the decomposition application, but this simulation has other application. For example, if you want to see a effect of a specific parameter, or I don't know, simulate the disease, see what's happening because of what that effect is happening, and all of these things can be simulated and learn more, but are focusing on the decomposition. So for the EMG signal, we have different models in literature. One of the most famous and most used is the convolutive model. And imagine that we have this motor induction potential that's recorded based on the location of electrode. We have the firing rate of a specific motor unit, something like this. If we convolve these two together, we will have a terrain of motor unit action potential that is or motor unit action potential trains. And if we put these trains together, it sums all of the trains that we have for each one of the motor unit action potential. In the end, we can create the EMG signal by summing all of them together. After using this convolutive model, we will sum all of the motor unit action potential together. We will create the EMG signal. And if we create this EMG signal with a low percentage for example, 10 maximum voluntary contraction, you can see that spikes are really clearly visible. And maybe it's really good for this template matching. If we have only one channel, we can more or less find by our eyes the location of different motor reaction potentials, and this template matching will work well. But if we increase the force to 30%, it's gonna be much harder. And in the 70%, that's almost all of the motor units are active. These the template matching and this type of algorithm or using it manually is not gonna really work in decomposition. So the simulation toolbox that we use is coming from this paper. They put the code toolbox in the GitHub, and you can find it in here with this link. Also, if you go directly to the paper, read the paper. In the paper, they mention the toolbox, so you can get all of the code, everything from that. So generally for simulation, this is the block diagram that I created. Maybe you can make some of them or create some more, but I think these are enough and good. In simulation, at the beginning, we need some excitation signal, and this excitation signal is more or less the signal that we want to produce in our mind, the time that we want to do some contraction. Or if we are in an experience and they ask us to do some percentage of maximum voluntary contraction, something like this, we need to increase the force more or less linearly to a certain level and then keep it constant, and then at some point decrease it to the zero. In this increasement part is the recruitment threshold part. Is usually the part that different motor units will recruit it, and every time that they recruit it, the firing rate starts from a point and it will increase until a point that, for example, in here is 50%. That in this 50%, the assumption in this type of simulation is that in here we don't have any more recruitment or de-recruitment, and the firing rate we're not gonna change a lot based on the fatigues and all of these things. So this is important to know. And when we are arriving at the end of the constant force, we have a de-recruitment process, more or less. We're decreasing the force. The different motor unit will de-recruited until the end that we don't have any active motor units and we don't produce any force. So after that, we need to simulate a muscle. The simulation of muscle, we need to specify exactly which muscle that we want to target. We need to consider the firing, the muscle fiber of that, and specify the conduction velocity, the diameter for each one of these muscle fibers, because these are the important parameters that can affect the shape of motor unit action potential later. Imagine that this is the picture of our muscle hands. And in this study, we are trying to simulate this small muscle here, abductor digiti minimi. So if you measure it by yourself or checking in literature, generally on average, it has a length around 70 millimeter and radius of 5 millimeter. And we can consider it has a cylinder shape. So if we create a cylinder like this, and we change the size to put it in the hand, it can perfectly more or less fit into the hand, and generally this cylinder shape is the acceptable shape. So based on the literature, we found out that it's more than 72,000 muscle fibers are in this muscle, and if we put all of them into our muscle, this cylinder shape, it can be fit perfectly if we look in the cross-sectional area. It's covered all of the area of the muscle. And after this, we need to specify a diameter for each one of these things. In the literature, they realize that this diameter generally coming from a normal or Gaussian distribution with a minimum of 25 micrometer, maximum 85 micrometer. So after that, we need to use this value into finding the conduction velocity. And the conduction velocity is specified for each one of the muscle fiber. Then it can cause that the action potential that produced in this specific muscle fiber is go faster or slower from each other. And again, based on the literature, they realize that the lowest conduction velocity in this normal muscle fiber of human is more or less around 2.2 meter per second, and the maximum can be around 5.5 meter per second. So after that, to create our muscle, we need to consider create the motor neuron pool. In motor neuron pool, we need to create and assign the recruitment ratio, de-recruitment ratio, the location of the territory center, the firing rate, and all of these things for each one of the muscle. So generally, the excitation signal is created here based on the muscle that we want to stimulate and we want to active. The location of the motor neuron pool is different, can be a spinal cord or brain. For all muscle, it is staying in the spinal cord. And if we consider this circle as our motor neuron pool, inside of it, there is a cell body of each one of the motor neuron or soma. And this line here is the axon of the motor neuron, which is coming from for our specific muscle coming from our arm. And these are the muscle fiber of our interest for this muscle. And these are the axon terminal, which is connected to this muscle in here. So they are coming from the spinal cord and connecting to here. So in the literature, they found out that the number of motor units or motor neuron, because each one of the motor units only has one motor neuron, so the number of the same. So for this specific muscle is 380, and we need to put all of them into the surface of the muscle. So we need to design where exactly to put them. The first thing that is come into our mind is to, okay, we need to distribute them uniformly. But in simulation, if we want to uniformly get a random variable from uniform distribution, it's not gonna work well. It's something like this, because it's usually random is uniform distribution for the bigger size. But with this limited amount of size, we need to use other type of algorithm, which this family of artist point algorithm, we can using with them to create a perfectly uniform shape for the location of the center of each one of the motor units. So after of that, we need to assign the recruitment threshold for each one of these motor units. So each pool consists a different number of motor neuron or motor units, which, for example, for this muscle is 380, and based on the specific contraction that you are doing in your exercise, you can activate a portion or whole of it. But for example, if you want to activate all of the motor unit in this specific motor neuron pool, you need to have a maximum voluntary contraction above 75%. These are the values that we create, we mention in the simulation, but in reality can be around this value. And you can check the list for the real value. But for example, consider that if we are contracting only 50% of the maximum voluntary contraction, we are activating these amount of motor units, and the rest of it will not gonna active. So in the EMG signal, if we record from all of the area of the muscle, in the best situation, we can see information of this part, not the other part, because it's not going to be active. So for the recruitment threshold in the literature, there are different models that were proposed by the Fuglevan and De Luca. So generally, based on the exponential shape, you can see the difference here in this specific muscle. We use the Fuglevan, of course. And after recruitment threshold, we need to assign firing rate for each one of these motor units. So these motor units that are in the beginning, usually they are a smaller motor unit. By mean smaller is the motor unit that consists only a few number of fibers. So if the time, there is a relationship, is go bigger, the recruitment threshold and the firing rate, recruitment threshold will be bigger, firing rate started later. So this motor unit that's gonna be active here, it increasing the force, we will have increment in the firing rate up to more or less this value, 45 hertz per second. For the bigger motor unit, these values can be lower. And for example, if we are contracting until 50%, these motor units generally will have a firing rate around this value 8, because they are big. So for the firing rate, we have also a different model, the Fuglevan proposed this model, and this excitation signal is the one that I explained a few slides previously. And so if our excitation signal is above the recruitment threshold of each one of the motor units, that motor unit will be active. And we have this value in this model, 8 hertz per second, 8 fire per second, which means that so the time that is above the firing rate about the recruitment threshold, it will start firing at this value, but by increasing the excitation signal for force, we will have increment into the firing rate. So DeLuca also proposed another formula, another model, and in their model they have different coefficients which they try to find the actual value based on the real signal. So if you have similar, if you plan to simulate similar muscle or this muscle, you can more or less use these values. But if it's new, you need to check literature if someone already did, or you need to do it, find the value by yourself. So in motor unit pool, we already have the muscle fibers. We already have the different aspects for each one of the motor units, and we need to assign this muscle fiber to the motor unit. We have these muscle fibers, and we have these motor units, more or less, the center of them. So for assigning to each one of the muscle fiber to each one of the motor units, we need to first see the size of this motor unit. If it is a big or small, based on the number, this is an important number for assigning different fiber to it. After that, we need to see how much these muscle fibers are close to the center of territory of each one of these motor units. And another important thing is, which in the literature is called self-avoidance. Usually a motor neuron will not get the muscle fibers that's more than a value that are close to each other. If some of them are adjacent to each other, try to get from another side or a little far. So this is a safe avoidance. And after considering all of these things together, we can have a probability for each one of the muscle fiber to be assigned to each one of the motor neuron. Then, after we do the assignment, we will have a shape like this, which is showing us all of the motor units and muscle fiber, which is not really visible. So because of that, I plot only a few of them. And you can see that we have a big motor unit, a smaller motor unit. These are the territory of the motor unit. They can be have a more or less, the territory can be interacted with each other. And the territory usually is the convex hull of the muscle fibers in the area. For example, if we have a fiber here, we have another fiber, we can connect all of these points together, the outer muscle fibers, and create the actual territory for each one of the motor units. So after this assignment, we need to assign neuromuscular junction location as well. So usually the time that the location that axon terminal are connected to the muscle fiber is a neuromuscular junction. And in this toolbox, they consider two until level 2 branching, which is this axon is branch 2 level. And we can have a different conduction velocity in each one of these levels. And usually they are connecting in the stimulation, more or less the main area is the middle of the muscle. And all of these neuromuscular junction came to an area surrounded by the middle, and to all of these locations, we are saying innervation zone. That is the zone that all of the muscle fibers are exist. But after creating all of these things, we need to record the signal. For recording, we need the electrode. And based on the shape of the electrode, the location that we place the electrode, and all of these things we have, we can record different shape for motor unit action potential. For the surface EMG, we have this good shape figure that it says that if the diameter is small, we can get much more information. But if we increase the diameter, we will act as a low pass filter. We will destroy all of the high frequency content. It's more or less similar in the, we have similar effect in the intramuscular. And in our study, we used one of the electrode that Sylvia, the real electrode that Sylvia already used. which is consists 40 different electrodes. Each one of these electrodes are separate each other from half a millimeter. In the toolbox, we can only simulate a point electrode, but because we want it to be real, we consider this shape, which is the shape of the electrode more or less, and we put 95 points, and we will get the average of all of that, the signal that recorded by each one of them, and we'll calculate the average. In reality, it's not like this. Each point is going to be an integral, but because the number of points is a lot, more or less is the same. So it's the good to take lots of points and you can get the same one. One thing that is important, each one of the electrodes, you can see that they are generally can get information from a motor unit that are close to them. So this electrode, if this is our interest electrode, it can see the motor induction potential of this motor unit, but if we go up, we are not seeing anything. Generally, these can be active, but we cannot record it with our electrode because it's far. Another important thing, if, for example, it's the same, but if we want, this is our electrode of interest, but if we see from different electrode, the shape gonna be different. And until we will see the motor induction potential on some different electrode, and after that, it will gonna be nothing. So we will see a specific the motor induction potential in a specific location for each one of the motor units, not all of the motor units. And another things that we need to consider in our simulation is the volume conductor. So imagine this, we recorded these two motor induction potential from the intramuscular recording. You can see that they are really different from each other. They have different shape. We can classify them easily by our eyes. It's really easy. But if we record them in the surface, they are passing through a fat tissue. This fat tissue remove all of the high frequency content. And in the surface, they are more or less similar. And it's not easy to separate them from each other, especially with this template matching technique. I think we will get nothing. And you can see also the time support, the time support increase as well. They are very shorter spikes in intramuscular, but they are bigger in the, and all of these is effect of the filtering and the volume conductor. Of course, in literature, they model these things as well. You have this multi-layer volume conductor that based on the location of your electrode, you can record, you need to simulate different paths for the motor reaction potential, for example, from this specific fiber to your electrode of interest. And we have a more complex version, which is the cylindrical, and they consider the 3D shape, and they try to calculate volume conductor in all of the aspects. But in this toolbox, which is focused on the intramuscular, the only things that can be that's done is the effect of electrode, which is, of course, can be considered as a part of volume conductor. But none of these things were simulated. And in the end, after simulating all of these steps, we need to generate our signal. And for generating our signal, so we need to first generate the motor induction potential. And imagine that in here, this is the neuromuscular junction, or from the muscle fiber point of view, is our end plate, that the signal or pulse arriving this point, and if it is more or less in the middle of our muscle in the study. And you can see by increasing the time, the action potential is try to go to all of the muscle fibers, to the location of the muscle fibers, until it's reaching to the tendon, to the both end of the fiber. If we plot all of the single fiber action potential for each one of the motor units, we will have a shape like this. You can see that each single fiber action potential is different. And for creating the motor unit action potential, we need to sum all of them together to have a motor unit action potential, something like this. And for generation of EMG signal, as I explained in the beginning, we have this convoluted model, which we can use this generated motor unit action potential and convolve it with the firing rate, and finally have a EMG signal based on the percentage that we want. So, any question?